In this program, I'll be discussing the flowchart preparation techniques presented in the EPA training manual titled Air Pollution Source Inspection Flowcharts. These procedures will be illustrated using this mobile hazardous waste incinerator system, which is processing contaminated soil at an abandoned chemical plant. The inspection flowcharts are designed to help you more effectively evaluate the plant operating conditions which affect compliance and to more easily recognize and avoid health and safety risks. In most cases, these flowcharts will also help you reduce both the on-site inspection time and the report writing time. The flowchart uses a block diagram format for major equipment. Units such as the kilns, evaporative coolers, and other large system components are shown as blocks. The shading is helpful in distinguishing the major equipment from other symbols to be added later in the program. Fans and stacks are types of major equipment which are especially important to air pollution source inspectors. For this reason, they are shown as indicated here. They are also lightly shaded for easy identification. This is the complete set of major equipment items at the example facility. A soil dryer and preheater, a kiln for oxidation of the contaminants, an evaporative cooler to protect the downstream air pollution control equipment, a set of pulse jet bag houses for dust collection, and an induced draft fan and a stack. In addition, there is an extensive soil excavation and handling operation and a plant control room mounted in a trailer. Gas flow streams are shown as two parallel lines. Sections of ductwork going from one piece of major equipment to another are identified using alphabetic characters. Here the section labeled B represents the duct from the kiln to the top of the evaporative cooler. Important solid and liquid flow streams are shown as solid lines with arrows indicating the direction of movement. These lines are assigned unique stream numbers which are placed in diamonds along the stream lines. In this case, stream 1 is the soil feed line from the dryer to the kiln, and stream number 2 is the treated soil line leaving the solids cooler portion of the kiln. It's important to remember that it is not necessary to show all of the material streams in a complex system. Only those directly relevant to the inspection should be included to avoid cluttering the drawing. In addition to the major liquid and solid material flow streams, a number of utility streams are also generally of interest. In the facility being shown here, some of the important utility streams include natural gas fuel for the kiln burner, fresh water for the evaporative cooler sprays, and compressed air for the cleaning of the pulse jet bag house. Only a portion of these lines are shown to avoid cluttering the drawing. A set of symbols for the various types of utility streams are shown on the back of the blank flowchart forms. It should be noted that these utility streams are not generally assigned identification numbers since we are not usually interested in the material flow rates, just the physical characteristics such as the pressure and the quality. The next step in the preparation of the inspection flowchart is to put on symbols for all of the on-site instruments which provide data for the inspection. It's important to remember two things about the instruments. First of all, many complex facilities monitor numerous parameters, and many of these are not relevant to the inspection. Include only those which are truly important to the inspection scope. Second, some of the plant's instruments are not monitored in the control room. These must be found while walking around the equipment. For example, this is the compressed air pressure gauge on the pulse jet bag houses, and this is not monitored in the trailer control room. A set of symbols presented on the back of the flowchart form is used to indicate the most common type of instruments. The locations of these instruments is indicated using dotted lines to either major equipment pieces or material flow streams. In the example case, there are temperature gauges and pressure gauges in several locations along the gas flow streams. To complete the flowchart, it is necessary to identify any sites for visible emission observations such as stacks and fugitive emission sources. These sites are identified using inverted triangles with codes starting with E for stacks and F for fugitive emissions. In the hazardous waste incinerator, these emission sites include the material excavation and processing operations, the treated soil storage piles, the kiln, and the stack. This is the complete flowchart for the hazardous waste incinerator. This is combined with health and safety information and baseline data obtained from previous inspections to complete the form. The remainder of the videotape illustrates the usefulness of the form during a routine Level 2 inspection. While preparing for the inspection, a photocopy of the flowchart from the previous inspection should be made and reviewed. This will provide some of the information to determine what safety equipment will be necessary for walking around the site. In this case, the plant is handling soil contaminated with several non-volatile carcinogens. Obviously, protective clothing, gloves, and respirators will be necessary. The inspection itself would start in the control room where most, but not all, of the operating data is available. This data is written directly on the flowchart next to the appropriate instrument symbols so that it is possible to quickly scan the data for obvious errors. There should be logical patterns to the gas temperature, gas stream static pressure, and gas stream oxygen profiles throughout the system. This is a plot of the gas stream temperatures in the hazardous waste incinerator. The data appears to be correct in that the hottest temperature is at the kiln outlet, and the values become progressively lower as the gas stream proceeds through the system. This is the static pressure data for various monitors along the gas flow path. At the kiln, the static pressure is about minus 0.10 inches, which is a typical draft for most combustion processes. The values become progressively more negative as the gas stream approaches the fan. Following the fan, the static pressure is slightly greater than ambient levels. This data again displays a logical pattern, therefore I'll accept this data as adequate. As long as the data appears to be reasonably accurate and logical, it can be used to evaluate the present operating conditions. During this time, the exit gas temperature leaving the kiln was 819 degrees centigrade, which compares well with the baseline data obtained during previous inspections and also the trial burn tests. Accordingly, I would conclude that the contaminants in the soil were being adequately destroyed at this time. The gas temperature drop across the evaporative cooler is in the range of 400 degrees centigrade, which is equivalent to about 720 degrees Fahrenheit. This indicates that the evaporative cooler is doing its job and that there is no need to check the spray nozzles at the top of this tower or the characteristics of the spray water. De-emphasizing this portion of the inspection saves time and also reduces the inherent risks involved with walking around the equipment. Considering the static pressure data written on the flowchart, it's hard to understand the reasons for the fugitive emissions from the kiln and transition duct up to the cooler. It's possible that the kiln draft gauge reading of minus 0.10 inches is actually an average reading and that there are some short-term fluctuations to ambient levels or even slightly positive levels. These apparent emissions should be evaluated further as long as the area of the plant can be approached without any undue risks. Further downstream, the flowchart indicated a baghouse inlet gas temperature of 204 degrees centigrade, which is very close to the maximum temperature limit of the Nomex cloth. The baghouse outlet gas temperature shown on the flowchart was 176 degrees centigrade, which suggests a very high temperature drop of 28 degrees C, which is probably due to air infiltration into the baghouse. Also, the Nomex cloth is known to be sensitive to hydrochloric acid and moisture, and both of these would be present in the gas stream entering the baghouse. And for all of these reasons, the baghouse performance and condition should be carefully evaluated. A check of baghouse operating conditions indicates a compressed air cleaning pressure of approximately 95 psig, which is relatively high. This could indicate intense cleaning. Furthermore, the static pressure drop calculated from the flowchart indicates a maximum of approximately 2 inches, which is relatively low. Both of these values suggest possible overcleaning of the Nomex bags. This could certainly contribute to frequent bag failures and may also cause seepage of dust to the fabric. The visible emission observation is obviously important since there are concerns about the operation of the baghouse. Obviously, in this case, the opacities were well within the regulatory requirements, and the opacity was less than 5% at the stack discharge. A check of clean side deposits provides an indication of emissions which may have occurred in the recent past. However, the high gas temperature written on the flowchart serves as a reminder that the observation hatch on the roof of the baghouse is in an unsafe area and should be avoided. Fugitive emission observations for the various contaminated soil transfer steps should also be included. The health and safety information above the flowchart provides a reminder of the importance of the safety equipment. It also indicates the need to go through decontamination prior to re-entering the facility offices or leaving the site in the agency's car. When the inspection is completed, the salient inspection data and observations should be written onto the flowchart form. This form should then be attached to any written comments in the inspection report. By using the flowchart form, any misunderstandings concerning the inspection date are minimized and the report writing time is reduced. In summary, a conventional block diagram type flowchart is very useful for the inspection of air pollution sources. The flowchart helps inspectors review sets of data and determine where to devote the limited inspection time. By placing the baseline data on the same page, it's possible to identify any shifts in site-specific conditions which could represent present or future compliance problems. The presence of the data in a very concise, uncluttered format helps inspectors minimize health and safety risks. Furthermore, the form provides a useful means to minimize inspection report writing time.